So, as I said that determination of this rate constant is very important and is one of the most important tasks of a chemical kineticist. And a combustion chemical kineticist, there are many very famous combustion chemical kineticists who are involved in determining rate constants from theoretical calculations, of course, by computation and theory. Okay. So, we will talk about two basic methods by which the collisional theory of reaction rate and the transition state theory of reaction rates. Using these two basic theories, we can essentially compute rate constant. These are very fundamental methods, and some of these gives accurate rate constant, some of these does not give accurate rate constant, but it will give you a basic idea of how to estimate rate constant. But more importantly, what this gives is that what is happening at a fundamental level. Okay. With this derivation of this rate constant, we can understand that how are these reactants actually going to form products, what is the mechanism. Okay. So, we always talk about this reacting with that, this reacting with this, but how does this reaction happen, okay, and how do we develop a model to describe that those reaction rate constants. So, for this collision theory of reaction rate, okay, we will talk about we will make several assumptions. We will assume that these molecules, which are like hard spheres, as we see in assumption 2, they follow this equilibrium Maxwell-Boltzmann velocity distribution. Okay. And number 3 is that reaction occurs, this is a very important assumption, reaction occurs if collision energy exceeds the activation energy, and by collision energy we are only talking about translational energy. Okay. That is two hard, essentially like two molecules, like two billiard balls comes and collides, and if the collision energy, if they have sufficient kinetic energy associated with this translation energy, and if the translation energy large and greater than the activation energy of the reaction, then the reaction happens. Okay. You see, but first itself you see the basic inherent assumption is that even though reaction and formation of new molecules means arrangement and dearrangement of the different electronic structure, here we are considering none of that, that as long as the collision is hard and it exceeds certain the activation energy, new molecules are being formed. Okay. And essentially this activity will be centered on finding the collisional frequency. There is a number of, in a given box, how many collisions take place, and that we will essentially, you will see that we will associate that with the rate constant, and that will give a very nice enlightening answer. Okay. So, what is the requirement of collision? For collision, of course, you see that this molecule comes and it must hit with this molecule. Okay. Of course, if they are head on, collision is guaranteed, right. But if you replace this molecule with little bit offset, this is still also guaranteed. So, the question is that what is the limiting condition in which collision is guaranteed? The limiting condition you will see is this, where this molecule comes in this way. This, let us we can consider, instead of considering individual velocities of the molecules, we can consider that this molecule J of the species J is fixed, and that of the species I is moving, and essentially the relative velocity with which the species I molecule approaches the species J molecule is essentially Vij. Okay. And for that, the limiting condition which will guarantee a collision, at least in some part, here it will happen tangentially, is that if these molecules, if at least half of these molecules belong to a collision volume. Okay. What is the collision volume? The collision volume is essentially this hypothetical cylinder which has a radius given by this. I will elaborate this. Okay. So, let us consider this as the central line of my molecule I. Okay. And for collision to happen, the molecule J must be situated somewhere here. Okay. So, that the center of this molecule J must lie within this domain, within this volume, which is this. Okay. And this is sigma I, this is sigma I by 2, because sigma I is the diameter of this molecule, sigma j by 2 is the sigma I is diameter of this molecule, sigma I is the diameter of this molecule, sigma I by 2 is the radius of this molecule. Similarly, sigma j by 2 is the radius of this molecule. So, the at least the center of the second molecule must be contained inside this collision volume for reaction to happen, and then this one is moving at a velocity Vij, which is the relative velocity. Okay. What is Vij? Now, Vij cannot be arbitrary, okay, because as we have said that we assume there is equilibrium Maxwell-Boltzmann distribution. So, then by Maxwell-Boltzmann distribution Vij has a definite form, which it comes from essentially the distribution of the velocities, and from that PDF of the velocity we can obtain the mean velocity, which is equal to 8 k 0 times t divided by pi times Mij to the power of half, whereas Mij is equal to Mi Mj divided by Mi plus Mj is called the reduced mass. Okay. And in this definition, of course, you see that k 0 is the Boltzmann constant, T is the temperature, pi is pi, and Mij is the reduced mass. Okay. Now, so first let us find out the diameter of this collision volume. Okay. The volume or the diameter is of course given by sigma I plus sigma j. What is the volume of this? What is the volume of this collision volume as such? The volume is given by is essentially the volume of the cylinder, which is given, say the Vc is given by then pi sigma ij square, whereas sigma ij is essentially sigma I plus sigma j by 2 times V I j average. So, what this collision volume means is that it means that in 1 second the second molecule must be inside this collision volume with respect to the first molecule. Where does Vij comes in? Vij is the distance covered in unit time. So, while this can be the separation in terms of their radius sigma ij plus by 2, in terms of their center to center distance they can be separated only by Vij in unit time. Sorry, let us average on unit time. So, if there has to be a collision in 1 second, the criteria is that the second molecule has to be inside the collision volume of the with respect to the first molecule of I, and it has to be the distance between these two can be at most Vij for collision to happen in unit time in a 1 second. All right. Now, let us say we will just remove we will go all this, and let us say now we are considering a box of unit volume V equal to 1, which can be 1 cubic meter, 1 cubic centimeter, etc. So, and this contains Ni number of molecules of I and Nj number of molecules of J. All right. So, you see in Vc volume, which was given by pi sigma I j square times Vij, there was one collision and it involved a collision between two molecules. Okay. So, basically for one molecule of I there was another molecule of J that guaranteed this collision. But in this volume V equal to 1 there are Nj molecules of J, right. So, in this volume now Vc the total number of molecules of J that is present is nothing but pi sigma I j square V I j times N j. Okay. So, these many number of things can happen. That was the limiting condition. In V equal to 1 there can be N j molecules. So, in V equal to V c there can be this many number of molecules of J, and as such this many number of collisions of the molecules of J with one molecule of I, right. So, for one molecule of I there are this many number of collisions happening. So, what is the total number of molecules of I now? Ni. So, the total number of collisions happening in 1 second is given by this pi sigma I j square V I j times Ni N j, okay. And that we will represent by this frequency called Z I j, which is the frequency of collision. We can also think that this in a different way, we can also think that this volume V c is essentially sweeping through our unit volume, okay. So, in one volume, as I said, in V equal to 1 there are N j molecules present. So, inside this V c volume there are in total this many number of molecules present, okay. So, there are for each one molecule of I there are this many number of collisions, but we have Ni molecules of I. So, the total number of collisions between I and J is nothing but pi sigma I j square times V I j times Ni N j, okay. So, these are the number of collisions in unit volume per unit time, okay. So, this is the essentially called the collision frequency. Now, we will just do this little we will shift gears and go through this analysis, but in this analysis the most important part is essentially this part, and there is another conceptual part which we will see immediately. So, what we have found is that we have defined this reduced mass M I j is equal to M I times M j divided by M I plus M j. We have defined a collision diameter sigma I j is equal to sigma I plus sigma j divided by 2, and we have got this collision velocity which comes from the Maxwell-Boltzmann distribution, which is given by V I j is equal to V I j mean is equal to 8 k 0 t divided by pi M I j to the power of half, and we have obtained the collision frequency for unit volume given by Z I j is equal to pi sigma I j square N I N j times the mean V I j, which is nothing but 8 k 0 t divided by pi M I j to the power of half. Now, so there are in total per unit volume this many number of collisions are happening per unit time, but all collisions do not have sufficient energy, right. You remember the postulate, the assumption number 3, that only those collisions which have an energy exceeding E A will result in reaction. So, how many molecules, how many numbers of molecules does exceed this energy E A? That is given by Boltzmann distribution, which says that this Ni times N star by N is essentially given by e to the power of minus E star by R 0 t, okay. So, we can find out the collision frequency of those molecules which have got energy in excess of E A. So, we define that collision frequency is given by this Z I j star, and these are those molecules, those number of molecules which have energy exceeding E A, N I star and N j star, and that is essentially if you substitute this guy into here for Ni star and N j star, you will find with this. Now, what is the collision frequency of Z I j which results in reaction Z I j star? That is nothing but your minus of d N I dt is equal to your minus of d N j dt, going back to the generalized formula for species consumption rate that we have defined, okay. So, then we can equate this to this, and and we can essentially using that we can equate this with this as we see, and now we can relate Ni with the concentration, because Ni is the number of molecules of I, which if you divide by the Avogadro number, which is the total number of molecules present in a unit volume, okay, or a given volume, as such we can find out the concentration, and then as such we can relate dCi dt to omega, what is the reaction rate, and we find that the reaction rate is given by this. Okay. This, as you see, this comes from the mean Vij, this comes from the diameter of the collision volume, A comes from the conversion factor between C and N, concentration and numbers, and Cij Cj comes from Ni and Nj, Ni and Nj star, and this comes from the fact that only those molecules, only those collisions which have an energy exceeding Ea can result in reactions. And if you summarize this, what you will get is a very nice looking relation, which is AT times Ci Cj and e to the power of minus Ea by R0t. Now, does not this look, this looks very similar to our expression of omega is equal to the by which we have obtained by the Arrhenius law as A times which is omega was like this, right, K for this Kf times Ci Cj, and that is equal to A times e to the power of, if you put Ci Cj now, Ci Cj times e to the power of minus Ea by RT. So, this frequency factor, if we compare between this one and the AT that has been obtained, which is essentially this, we find that the frequency factor is given by this formula. Okay. So, you see that this collision theory nice has a very nice correlation with the Arrhenius law as such, and the law of mass action, right. So, now unfortunately in some cases, for example, if you consider something like a reaction involving say hydrogen iodide decomposition of 2Hi, something like 2Hi something like if you see this reaction, if you see say 2Hi goes to H2 plus I. Now, if you compare the sigma for sigma Hi, and if you find out the mass of the reduced mass of H and I, and if you find the K0 and if you find A0, you will find that the reaction rates has a very nice the reaction rate that you obtained from this has a very nice relationship with the experimental obtained reaction rates, but this is not always the case. The primary reason is that you see that we have made very simplified assumptions. We have assumed that as soon as there is a head on collision, that is enough to guarantee reactions, but reaction is much more. It, as I said, that reaction means in the change of the orbital structure, the electronic structure changes during reactions, right. So, one species becomes some other species. So, the electronic structure changes, and also there can be other components of energy involved also, not only translation, there can be rotational energy involved, there can be vibrational energy involved, and also the molecules need not be hard spheres, right. In fact, most molecules, say the hydrocarbon molecules, methane, ethane, propane, butane, all of this and even higher on, they have very large complicated chain type of structures. So, this assumption that these two hard spheres collide and immediately react when the Ea is greater than when their translational collisional energy is greater than Ea, that is a little bit too limiting an assumption, and as such it does not obey the theory all the time, but it gives you a very clear idea of how to approach this problem and what is essentially happening. And the deviation of this theory can be accounted from this steric factor, that is equal to z times I, but we will not go into this here.